way to remember him, I think, well, let's talk about mathematics. All right. So this announcement, I hope you all took a look. So the title of my talk, from quantum group to iQuantum group. So I will explain what iQuantum group means, but starting from quantum group. Well, given a simple algebra like ACO2 or ACON, you can define the associative algebra, universal enveloping algebra, U of G. So quantum group, which was introduced by Greenfield and Jimbo in 1985, is a quantum deformation of the enveloping algebra as a Hopf algebra. This kind of Q deformation philosophically appeared earlier in mathematics, in representation theory. That was due to Iwahori, and this is known as Heck algebra. This is a Q deformation of wild group algebra. Or take the example symmetric group, and then you can write down n factorial dimensional algebra like this. The split relation is the same. The quadratic relation changes a little bit. And there's a Q there, which when you set Q equal to 1, that quadratic relation go back to the usual simple reflection relation. That's all familiar. So to our audience, we don't need to go much further. Well, let's come back to the quantum group. And first thing we all know, quantum group is not a group. So it's an algebra defined using generator relation. And generalizing the usual set representation for the semi-simple algebra or the corresponding enveloping algebra. The generators, they are parameterized by the simple roots. Now typically write capital EI, FI, KI. The Cartan part KI in the quantum situation becomes invertible. Okay. They satisfy some relation I'm not going to write down. They are fairly similar to the usual algebra relation. And quantum Q-set relation, we'll see it at some point. Okay, so the simplest case, the quantum group, quantum ACO2, in this case, you don't need a Q-set relation. So you just have EFK generator, and the relation EF commutator is given by K minus K inverse over Q minus Q inverse. So you roughly want to think K is Q to the H is the algebra Cartan. When you set Q equal 1 limit, you will recover the usual ACO2. U is a Hopf algebra with co-multiplication, delta, from U to U tensor U. So this key to the quantum group is the non-commutativity of the co-multiplication. So co-multiplication is not equal to co-multiplication when you swap the two tensor factor. And this co-commutativity, when you first see it, it's a little strange and took a while to get used to it. But this is really the key, for example, for the application of quantum group to quantum topology. Without this property, you cannot do much. Well, and the quantum group really has been so influential. I think when I was in graduate school, I was learning this, I simply didn't get it. These things, what's going on? Why bother? The formula, all formula become more complicated. They are different Q powers there, and so on. And it took a few years to get used to it. And then you realize all those Q power make perfect sense. They have meaning. And they have categorical meaning. They have geometric meaning. And so this quantum group turned out to be really deep subject. It's a shadow of much higher, deeper categorical structure. Okay, so, well, I hope if some of you are not working on quantum group yet, and sooner or later you might get infected. Well, a better question to ask is not what is quantum group, which we already finished the talk back then, and what is good for? Well, number one, helps when fields metal, help produce lots of math jobs. Well, a little more seriously, application to, these are already 4 different areas: math physics, representation theory, quantum topology, algebraic combinatorics. And not many new concepts has such an impact. I certainly cannot easily come up with another example. Okay, so I'm not an expert on anything else. I only know a little bit about representation theories. So let me tell you a little bit more about what quantum group good for in representation theory. I will make up a personal top 10 list. And this is really a who's who list in quantum group in some way. And also this list is totally subjective. And you are welcome to go home, make up your own list. Also not all the favorite subject topics may be covered in the coming slide. This list, I will go a little slowly. The first one clear. And then the R matrix was introduced by Greenfield exactly to solve this problem. The co-multiplication is not co-commutative. So that's the thing. You create a problem, then you solve a problem, and you want fields metal, okay? Then Lustig use this version of the R matrix known as quasi-R matrix to construct a bi-involution on the tensor product, then to construct canonical basis on tensor product. So it's useful. And quasi-R matrix, the difference only on the Cartan part. The essentially important piece is quasi-R matrix. Then that again go back to the first 2 papers of Jingbo, quantum sure duality. And then there's the work of canonical basis. And this is a basis for the quantum enveloping algebra quantum group. But this basis is new even at Q equal 1 when you talk about basis for the enveloping algebra. This is a basis which is so powerful. And if you talk about those, say, finite type, all those finite dimensional simple module of a quantum group, it allows you to obtain a uniform basis on every module. These modules are quotient of the quantum group. And I like to call this is a linear algebra student gene. When you have a quotient map from vector space to another vector space, you have a basis on the bigger vector space. The non-zero image is a basis on the vector space. Our students love to write down statement like that. Which is most often is not true, unfortunately, in their situation, and that's very rare. But it turns out for quantum group, this canonical basis, this fact is true. The non-zero image forms a basis. And this canonical basis, of course, has so many applications I'm not going to mention, but only one which was used to formulate a super-Cauchy-analytic theory for the Lie-Super algebra. And this, for the super algebra, the usual Cauchy-analytic theory using Heck algebra cannot work. But turns out, thanks to the Q-sure duality and such, you can switch to a quantum group side, use canonical basis to do the job. So to me personally, the items 2, 3, 4, 5, they are all related, but they go to different generality as well. We'll come back to this. And also, of course, there's a famous Hall algebra construction due to Ringo, and then there are different versions, geometric version, Lustig. Then only 20 years later, Bridgeland did a Hall algebra construction for the whole quantum group. The earlier construction of ringo-Lutic, they only did a half quantum group. And quite a few people wanted to do the whole quantum group in the meantime, but didn't manage to. Then a fine algebra, a fine quantum group, they always in their own world, they are incredibly rich, and they have connection like vertex algebra and other things. And so just like the Lie algebra, a fine quantum group has a loop representation. That is crucial for the representation theory of fine quantum group. Then you have the braid group action, and that's useful for constructing PPW basis and canonical basis, and then geometric realization. And they are different construction, different generality, using type A flag variety, Billingson-Lutic Matheson construct quantum group type A geometrically. Then Nakajima can realize using his quiver variety, more generally, a fine or loop cosmology, quantum loop algebra. And then, of course, the last 10 years or 12 years now, categorification is getting extremely powerful and popular, and due to Kovanov, Lauda, and Weiqiang. They categorify the quantum group. Really, what we saw before, quantum group, they are positivity, things are structure constant, are integral, and so on. So these are all because they are Grothendieck group of something. All right, and your favorite might be hidden there. So also let me quickly add, there are different interpretations of the quantum parameter Q. One in the geometric construction can be counting over finite field, so cardinality of the finite field. The other interpretation is in terms of equivalent K theory, then Q arises as the C star action. And so if you do K theory over a base point, you get the base ring or long polynomial ring. And a deeper interpretation yet about the Q is it counts a C gradient, okay? And this approach becomes clear in this categorization. Now let's move on from quantum group to iQuantum group. Since I don't assume there are many experts here, let's start slowly. If iQuantum group in its classical limit, this part turned out to be really classical. It's known as symmetric pair. And this go back to Elie Cartan even. But we are not going to tell you a lot about this. The group version, this real group, and this Cartan involution, some version of those. And I would rather talk about the algebra version, okay? So G is semi-simple algebra over complex number. You have some involution and talk about fixed point subalgebra K. This K is often a complexified version of the algebra of some compact group. For example, you can take this involution to be the Chevalier involution. That's basically the conjugate, transpose of the matrix in the case of matrix Lie algebra after sign. And so switch the Chevalier generator EI and FI after sign. The sign is not important, but HI will go to minus HI. And though the fixed point subalgebra in this case is generated by Fi minus EI. In the case if the G is SLNC, this Lie algebra is SONC. But this typically, the setter generator I write down is not the setter generator you learned in semi-simple Lie algebra. Okay? When we do a semi-simple Lie algebra for orthogonal Lie algebra, we typically don't want to take the binomial form whose matrix is identity matrix. You look at Humphreys, you always do a different matrix. And this matrix is bad, but it's good. Again, you come back to the life when we want to talk about the iQuantum group. Okay, so here's a quick list, but it's not important. You want to remember the very first case is all you need to know. ACONC, you take the fixed point subalgebra under minus conjugation. That basically give you the orthogonal Lie algebra. Okay, and it includes both type B, type D. There you can do a little more complicated involution, such as in the ADE case, you may have non-trivial diagram automorphism. You can compose this diagram automorphism in use, of course, the algebra involution. And you can compose then, this is involution, and you can talk about fixed point subalgebra. But anyway, there are more general examples of a symmetric pair. I'm not going to talk about there. Knowing one or two examples in mind is good enough. And Cartan classified all these, irreducible symmetric pair, and they are in bijection with the real form of complex simple Lie algebra. And if you are interested in like a thinking diagram classification, you can also draw thinking diagram, add some declaration to it. And this is known as Satake diagram. And the node, you need to color them as black and white, and depending on the situation. So each type you only could add a different color. And occasionally you allow the non-trivial involution of the diagram, tau in it. They need to satisfy some consistent condition. And it can be generalized to Kazamudi, let's not worry. So the terminology, we have seen it, quasi-split correspond to the case in the Satake diagram. There's only one color, only the usual white color. And split case correspond to, in addition, there's no diagram automorphism marked on the diagram. Okay. Every complex simple Lie algebra has a split form. So, but they could have other real form as well. So there are quite a few Satake diagrams in only infinite type. Many modern thinking diagrams. Now I give you a quick definition of iQuantum group in the special case of a quasi-split. So you start with your quantum group U with generator EI, FI, KI. And this was introduced by Gail Lester around 2000. And this is known as quantum symmetric pair. So first one is quantum group U. The second one is UI. UI by definition is a subalgebra of U. And satisfy one additional property called co-ideal. That is that condition under delta. Delta send UI to UI tensor U. The second characterization you want is this at classical limit, it's the usual symmetric pair. Okay. And so for us, we will just call UI an iQuantum group. So this is a quantum algebra. The first definition is a subalgebra of quantum group. And Lester motivation is very different from nowadays, what we are getting into. He comes from harmonic analysis of quantum symmetric space. Okay. So a quick example is, well, that's the only honest example I write down, a quasi-split iQuantum group. So in this case, Cartan part, forget about that. And then the new generator, you need to mix F and E. Even you take tau to be identity, you need to add FI to EI. That's a typical thing we saw, or minus EI, but we allow a little variable there that the plus minus sign is not important. As a check algebra, they are all isomorphic. Turns out. So we have a little parameter here. And quantum case, turns out is crucial. You add the KI inverse there. In Q-equal limit, you don't see it. Okay, that's it, just given by some formula. You define some subalgebra. A priori, this is nothing terribly clear. This algebra has biggest significance. And nowadays, we take the view the iQuantum group is a faster generalization of quantum group. Just like the usual real reductive group is a generalization of the consideration of a compact Lie group, if you like. And the real group, you can also embed into a complex Lie group. So in that sense, you can define a subgroup. So this analogy is fairly similar. There are two cases actually. Quantum group arises as an example of iQuantum group. This case is totally trivial, but in the classification in terms of target diagram or the symmetry pair, that corresponds to the case, the involution is identity case. This case in some later work is still not a trivial case, okay? Another more interesting case is consider diagonal symmetry pair. You take a two copy of thinking diagram, disconnected, identical copy, and swap the corresponding vertex, give you an involution, diagonal involution. And the fixed point subalgebra is a copy of G. Turns out, you can quantize the above picture. Therefore, this diagonal subalgebra is really isomorphic to the usual quantum group U. So that U, that Y, the quantum group can be regarded as iQuantum group of diagonal type. So for those people who have been interested in quantum group, not seeing this iQuantum group quantum symmetry yet, basically you have been working with these two examples without being aware there's many more examples of the quantum algebra which are very interesting. All right, still let's repeat the question. What is iQuantum group is good for? Well, it's some short answer. This is much more modest. My students nowadays tend to write thesis on quantum symmetry pair iQuantum group. There are several applications in math physics, algebraic combinatorics, which I will not get into. Instead, I will spend my time explaining some applications on the representation theory, okay? And in the short answer, is the top 10 list I gave you, they all admit the I generalization. So if you like some of those items, you feel those are indeed some of the central construction of quantum group. Okay, let's see how this. So definition is defined as a subalgebra. Turns out they have some presentation, but it has a complicated story. Almost each item here, you can give a lecture series on those, okay? So let's not too worry about this. And this notion for analog quasi-R matrix, now they known as quasi-K matrix, introduced by Bao and myself. And this notion of generalizing Jingbo's sure duality, now they call it I-sure duality. Eventually, we get tired of it. We just add I everywhere if that's to name something. And this one has a further generalization in Yao Long Shen's work this year. I might come back to comment briefly that. And then I-canonical basis, there's a faster generalization of the canonical basis in this iQuantum group setting. The motivation for Bao and myself, we wanted to develop a supercardinal theory of orthogonal symplectically superalgebra. And for that reason, we developed the 2, 3, 4. So the 2, 3, 4, 5, they are related as usual. And they arise in Bao's UDA thesis. And then after that, you realize, oh, you don't need to concentrate on one particular type of A. And this is many things generalized to much more general iQuantum group. Then also you can talk about geometry realization. This is analog of Beilinson, Lewis, McPherson. They use type A flag variety. Turns out, if you ask the question for type of BCD classical flag, the quantum algebra you get is iQuantum group. It's not a quantum group of BCD type. This is a question I heard a little bit during graduate school in the early 90s. I think probably some student wrote it to try a little bit, but I heard McPherson after that paper try a little bit about this. What's the quantum algebra behind the classical flag? But that they were ahead of time. And also you can talk about QOR type of categorization. This I will come on later, but they are, it's promising, but also they are obstacle. This is one case which was done in the literature. Then the Hall algebra. Turns out this one is a little subtle, right? Our iQuantum group is analog of the quantum group, the whole quantum group, not half of quantum group. So for the usual Hall algebra, typically you construct for the half quantum group. We don't have that analog. And so our Hall algebra is analog of bridge line. Only after bridge line work, we can possibly talk about this Hall algebra. Okay. Then there's a fine iQuantum group. And Wei Nanzhang, my other student, who will give a presentation this afternoon. I think you might hear more about this. And again, the answer, once you formulate it right, is completely natural. And yeah, but it takes work. This is something coming soon. This is something I'm very proud of. We now did most of the work. Now we can develop a fairly intrinsic approach to the group action on iQuantum group associated to the so-called restricted Wang group. This is known in the setting of symmetric pair. Yeah. Okay. So this is the generality I want to talk, but I will get down to specifics soon. Before getting there, just a little story. And so Huang Chenbao, before coming to UVA, he didn't know if anything about representation theory, symmetrical algebra. He all learned all this in the first year in graduate school at UVA. And our first paper finished in his third year. And this is a long paper. And I even still consider this is a paper most significant with my name attached to it. So this served the problem solving an open conjecture, not conjecture. Conjecture was not even formulated. We formulated and solved it using this I-canonical basis arising from iQuantum group. And to me, this is a very special case. What's most important about this is really we start seeing why iQuantum groups are important for many other things. We will come back to this. Well, yeah, that's something I like to say to a student. Yes, you don't need to know a lot to start with, but if you have the right problem, you do hard work, you sometimes in 3 years, you can do something I can not do, never do alone in my lifetime. Okay. So what's this, I like some of my friends also refer to as I program. And I like to serve as a slogan here. iQuantum group is a quantum group for the 21st century. A little more precisely, I like to advocate basically all the fundamental construction in quantum group. The nature can vary, be algebraic, geometric, or categorical. You should aim at the I generalization. The top 10 list I give you are example of this, but also be aware, many items in that list, the answer is only partial. Only some cases, only very limited cases in that particular direction is known. So those are still, in the earlier top 10 list for quantum group, I could have mentioned hundreds more people there. These are just some very small list of people work I mentioned there. Okay. So also there are many more things. If you hear my talk in different time, my top 10 list will evolve. Okay. So before giving you some example, let me again see some things in general. This I generalization I want to emphasize, they are totally natural generalization of those construction in quantum group. But those things, when it's done right, they are totally natural. You specialize to the trivial symmetric pair or diagonal symmetric pair case, you recover those great work by those great people. Okay. But they are proof, they are often much longer, sometimes 10 times longer. Even statement may be equal length, you need to prove it longer. The reason, let me mention, in the real case, there are many real rank one, just like a real group. If you are familiar with, there are already, I could count, say 8 different real rank one. And for the complex case, for the usual or complex case, there's only one rank one SU2. So that makes life much easier. So many things reduce to rank one, right? So rank 2 is crucial for cell relation. The usual cell or Q cell relation are uniform. But turns out in the iQuantum group world, even now, still there are quite a few, they are better understanding now, there are still a few non-uniform ones around. And still they are debatable what's the right formulation. Different people give a different answer. And another crucial defect for iQuantum group is there's no triangular decomposition. That one is really bad. So everything you want to generalize things on U, not on U minus, U plus. And so if you want to do canonical basis, you cannot copy Lutik's procedure of Kashiwala, starting from U plus. This is one thing why in the earlier work, these things were missing. The integral form are not obvious at all. I will show you in an example at the simplest case, a real rank 1. And that's one reason, without integral form, you cannot talk about geometric structure, categorical structure, nothing. You don't expect, you don't suspect those things. Okay, now let's, in the remaining time, I basically want to show you some example and give you some application, which not necessarily the most important one, but I hope is easier from the perspective of the audience to see, okay? So let's recall quickly the usual rank 1 quantum group, quantum ACO2, the integral structure here. So ACO2 has a simple module of dimension n plus 1, highest weight n. That's called AON. And let's define a so-called divided power. This is using Fn divided by quantum n factorial. Then in this representation AON, you can also define integral form there. You start with high weight factor eta, you apply F, then you apply the higher divided power, F2 and F3 higher divided, excuse me, and take a linear span of this over the Laurent polynomial ring, CQQ inverse. And this is a good integral form in the sense the quantum group also has an integral form generated by the divided power. That acts on this integral form preserves the integral form of the representation. And this is a general statement even for higher rank. Okay, you can define, but of course definition will be much more involved. I only give you a little example. ACO2 case, you can just write down this by head. Detail won't take too much longer. Now let's talk about iQuantum group. I give you an example of so-called split rank 1. And in this case, the iQuantum group is subalgebra of quantum ACO2 with a single generator B. So abstractly, this is a polynomial algebra in one variable. How much simpler algebra can we get? And this generator, for example, I wrote down a particular parameter phi inverse, you can do something like this, but you can do variation. Let's not worry about that. So let's ask a question from the following way. Which element in the polynomial ring preserve that integral form of SO2 module, LNC? You start playing around. You want those elements with leading term is like a low-sig divided power. And turns out a new phenomenon shows up, parity. That's something which you never encountered in quantum group situation. Well, the first divided power, you just take a B. That's okay. B is integral. But so we start from the second divided power. So to imitate, you try to do B squared divided by quantum 2. Good. If you are lucky, having to start with even an integer, indeed this preserved. But if you check NR, this is not true. It's not preserved. And then you try the next one, the cubic power. Turns out by fooling around, you get something like this. B minus quantum 2 times B times B plus quantum 2 over 3 factorial. And the next one, you get multiply B in the middle, divide by 4 factorial. The next one, you remove that middle B, add a B, 2 factor B plus quantum 4, B minus 4 on the side. You see the pattern. Pattern is very clear and allow you to define general formula as. And then the claim is these elements do not preserve the integral form Ln if n is odd. For n is odd, you need another sequence. The second divided power, for example, B squared over quantum 2 will not preserve Ln if n is odd. You need to shift by 1, for example. It will work. If this works, the above definitely will not work because the difference of these two is 1 over quantum 2, which is not integral. You cannot have two correct answers. Okay? And this one also will continue. The thing is here, you are going to use all the quantum integer. The above, you use even quantum integer as your spectrum, as your roots of those polynomial in B. Remember, in low-sig divided power, f to the n over n factorial, all the spectrum is 0. This is a monomial in F. So if you want to talk about higher rank, you write B as Bi. And to remember which simple root I. Now, this is general formula I just wrote down earlier, but you can summarize. This is what we call I divided power. And this general formula in the case of even parity. They are closed formula you can write down. And also this can be redefined using recursive relation, very simple recursive relation. Okay? And this one, if you think B is F plus some term involving E term is lower term, so it has leading term F, and this new I divided power has leading term which is low-sig divided power. That's the one of the idea. And you can define another sequence I'm not writing down. I claim this I divided power, even if you are only interested in polynomial algebra in one variable, these are remarkable new bases. This basis has, for example, positivity, integral structure. If you multiply two such basis elements, the structures constant are positive integral. But they are minimal positivity. These come from the geometry. And this I divided power turned out to be the first concrete example of I-canonical basis. And the formula was more or less conjectured in the first paper with Bao. We know I-canonical basis exists abstractly, but we had a little difficulty checking these elements I wrote down is really integral. That appeared in my work with Berman. And basically we're saying if you apply the I divided power to the highest wave vector, the non-zero one form a basis. Let's forget about the non-I-canonical. The higher one vanish. And then if you just talk about this abstract algebra, iQuantum group polynomial ring in one variable, I obtain a basis. The basis is what I call the I-canonical basis. But it has two versions depending on the parity. This parity is some kind of idempotent which you don't see in the quantum group because this really doesn't come from the lattice. This kind of corresponds to some kind of torsion point. A little weird. Now looking back, this is another way you can discover this formula for I divided power from linear algebra. You ask yourself the question, as linear operator Bx on this n+1 dimensional vector space, what is minimum polynomial? And you go home, compute. I claim this is the answer. If at the Q case, I don't think the computation is too easy, but that's a part of the theorem. If you ask the question answer, you will find this formula. That's what I'm saying. And yeah, my course here, he was a UP undergraduate. For example, here we already have a question. If you try to categorize this polynomial ring in the sense of Covano-Lauda, okay, or even in the first paper of Lauda, of ACO2, but categorification is a subtle business. Okay. Now, let me mention the first application. This is kind of application paid back to the foundation of the quantum symmetry pair. Earlier work, there's already due to Gail Lester, there's some kind of set type of presentation around. But from her work, you can tell those set presentations are terribly messy, complicated. Okay, we'll come to that point. But for the usual quantum group, the relation are very uniform because the Q-set relation, no matter what are the Cartan integerCijs, you can write down this formula uniformly. In particular, if you write down in terms of the divided power, is as written, just alternating sign. Okay. Now, I want to have an analog of this theorem for a large class of quantum group. And this is true for split quantum group, but also can be easily generalized to quasi-split. I'm not touching here. In this case, here is the new version of the Q-set relation using the I divided power. Notice those index, I don't have a pointer. Those index, they are depending on the parity. The parity on the first divided power and the last divided power, they are different. They pass through the middle Bj, so the parity get changed by Cij, the parity of the Cartan integer Cij. But you can take a P to be 0, the even, this formula is true. You take a P to be odd, this formula is also true. So these formulas, they have two forms. Both are truth identity. And this formula is true for Alcatz-Moody. Okay? Why? If you like this formula basically look like the same as above. You want to compare earlier formula, like Lester. She computed for the case Cartan integer less than or equal to 3. Cartan integer equal to -1 case, I didn't tell you. The -2 case, if you try to write this set relation, the left-hand side like the usual one without using divided power, that's the form it is. Then you try to write the usual Q-set relation in terms of F, you replace the letter F by B. That's what the left-hand side look like. But the problem is the left-hand side, once you replace F by B, is no longer 0. And the answer is given what's written on the right-hand side. And I'm saying is because our I divided power is not a monomial in B, and they absorb the right-hand side term into the left. In such a way, the right-hand disappears. If you have a chance to look at the Lester formula for Cij equal -3, that takes 3-4 lines to write, which I'm not able to fill into this slide. The right-hand side will be very, very long. Okay, and from the formula, it's fair to say probably it's unlikely you can generalize the to Cij equal -4, -5 further. And our formula is a very simple one, uniform one. That's, I just want to say, this is the first application of the I divided power, but we discovered I divided power from I canonical basis. And the second application is this Schur duality I can mention a little bit. And this specify specialized to a very special case of iQuantum group called quasi-split type A3. You don't need to know exact definition what it is. The diagram show up in my title slides is the diagram of type A3 Satapi diagram. Anyway, so this is a subalgebra quantum ACLN type A, and V is the natural representation. And then we have the usual Jingbo duality. Quantum group and the Hecke algebra type A, they form double centralized when X on V tensor D. Our iQuantum duality is a generalization of this when you change the type A Hecke algebra to a type B Hecke algebra. Turns out you can formulate a version of this type B action with suitable indexing of the natural representation. And then turns out the double centralizer for the type B Hecke algebra, which is a larger algebra than type A, which now UI is a subalgebra U. And the claim this is iQuantum group type A3. And this duality was significant in the application to the Cauchy-Loomis theory, but let's not get into that. What I want to remark here is in the Yao Long's new work in the archive, turns out there's a new version of this iQuantum duality, which unify both Jingbo duality and this older version of iQuantum duality. It uses the type A3 iQuantum group of general case. And what's useful about this new general iQuantum duality, this leads to a new Hecke module of type B Hecke module, parameterized by coset associated to reflection subgroup, which is not necessarily parabolic. And this to me is rather astonishing. And this is, I think is new. So most of the consideration were parabolic subgroup. I have last slides. Basically, this one putting a bit more thing here, but I just mentioned this type A3 quantum group has application. This allow you to build up a new canonical basis on this mixed tensor space. Those one provides the right Cauchy-Loomis polynomial for the superalgebra OSP. And these slides are very brief. You don't have to remember that. And furthermore, you can go beyond from type A3 for actually iQuantum group. And we have developed a theory of canonical basis. And that is a generalization of Lustig for quantum group. Okay.
Let's thank you.